Hello, and welcome to the Quantum Slumber. I'm glad you're here tonight. Whether you're listening with your eyes open or already halfway into sleep, this channel is a quiet place for slow, calming science stories. The kind you don't have to try to follow. You can simply let the ideas drift past like soft light in a dark room. And tonight, we're talking about something that feels so familiar, we almost never question it: gravity. Right now, gravity is doing something very ordinary. It's keeping you in your chair, keeping the air wrapped gently around the Earth, keeping the moon on its quiet path, and guiding our whole planet around the sun as if those circles were the most natural thing in the world. And because it feels so familiar, we rarely stop to ask what gravity actually is. We learn a simple picture early on. Gravity is a force that reaches out, grabs things, and pulls them down. It's a clean idea. It works well enough for everyday life. Drop a coin and it falls, toss a ball and it returns. The world seems to confirm the story. But here's the thought that changes everything, especially once you let it settle in slowly. Gravity isn't actually a force, not in the deepest sense. What we call gravity may be something closer to shape than shove, closer to geometry than grip. The kind of thing that doesn't push you through space, but quietly decides what straight even means in the first place. And if that sounds strange, that's exactly why it's worth exploring. Because the same idea that explains a falling apple also explains the smooth, steady motion of planets. It explains why light can bend. It explains why time itself can run a little differently, depending on where you are. And when we follow it far enough, it leads us to the most extreme places nature allows, where space and time tilt inward, where the universe makes black holes, and where reality can ripple like a deep, slow tide. But we're not going to rush. We'll build the picture one calm step at a time, until the strange parts start to feel natural, almost inevitable. So if you're listening as you rest, just let your shoulders drop a little, let your jaw unclench. There's nothing you need to memorize tonight. You can simply follow the story. And if you drift off along the way, that's perfectly fine. And if you enjoy these quiet science journeys, you're always welcome to gently tap, like, subscribe, or leave a small comment. Maybe where you're listening from, or what topic you'd love to wander through next. It helps more sleepy minds find their way here. Now, let's begin with the simplest question. If gravity isn't a force, what is it? Most of us think that we already understand gravity, not because we've studied it deeply, but because we've lived inside it every day of our lives. Gravity is the most constant background sensation you've ever had. It's the quiet reason a glass stays on the table. It's why your footsteps have weight. It's why a tossed set of keys never keeps rising. You don't have to believe in gravity, you simply wake up inside it. And that familiarity creates a very specific picture in the mind. Something reaches downward, a pull, an invisible hand that tugs on objects and draws them toward the ground. It's an intuitive story, and it works well enough for almost everything you do. When you drop a coin, it falls. When you jump, you return. When rain leaves the clouds, it doesn't wander sideways forever. It comes down. Even your language reinforces it. We say pull of gravity. We say gravity pulls you back. We say what goes up must come down, as if the downness of things is a rule written into reality. And in the simplest classroom form, that's exactly how it's taught. Gravity is a force, a real force, like a push or a pull, like a rope but invisible, like a magnet but universal. And for centuries, that model was not only considered correct, it was considered one of the most successful ideas humans ever had. So why mess with it? Because there's a trap hidden inside any idea that feels obvious. The trap is that obvious things feel complete. They feel finished. They feel like the last page of the story. But sometimes, the most familiar picture is only a sketch, useful, accurate within its limits, and quietly incomplete underneath. A good way to sense that is to think about how the Earth looks. From where you stand, the world appears flat. The ground stretches out. The horizon is a clean line. Buildings rise straight. water in a calm lake settles into a level surface. Your eyes, your balance, your daily life all agree with the same simple conclusion: flat. And if you lived your entire life within a few miles of where you were born, and never saw a ship sail out past the horizon, and never watched the shadow of the Earth crawl across the moon during an eclipse, you might not only believe the Earth is flat, you might feel it. You might think, of course it's flat, I can see it. The mistake wouldn't be that the flat model is useless. It's useful. It's perfectly fine for walking to the kitchen. It's fine for building a house. It's fine for almost everything ordinary. The mistake would be assuming that usefulness equals final truth. Gravity is like that. The force story is useful. It's wonderfully predictive in the world of apples and basketballs and parking lots. But it isn't the deepest description of what's happening. And once you start noticing the edges of the force story, you begin to see why a deeper picture was needed. Let's begin with the simplest scene. You drop an object. A coin, a pencil, a small stone. It accelerates downward, faster and faster. Your senses report it as a reminder. There is something acting on it, something causing the change in motion. And because we're creatures who understand the world through touch, we imagine the cause as something like a hand, a pull. But here's the question that quietly sits underneath. How does that pull travel? What is it made of? How does the Earth reach across empty space and influence the object without any contact? That question used to be uncomfortable because for most of human history, forces meant contact. A push meant something touched you. A pull meant a rope or a muscle or a hook. If you wanted to move something, you had to interact with it. Gravity refuses that intuition. The Earth doesn't touch the moon, yet the moon's path stays bound. The sun doesn't grab the planets with a visible tether, yet the solar system holds together like a quiet clock. So in the force picture, gravity becomes a kind of action at a distance, a force that somehow exists in between, passing through emptiness, always present, always reaching. And again, in the daily world, you don't have to worry about how it works. It simply works. But when you slow down and look carefully, you start to notice that gravity behaves differently from the kinds of forces your body evolved to understand. If you push a shopping cart, you can feel the resistance. You can feel the friction. Your muscles tell you the interaction is happening. If you hold a magnet near another magnet, you can feel something too, an invisible resistance, a push, a tug. And if you bring them close enough, you feel it strongly. Gravity doesn't announce itself like that. You can stand next to a friend, shoulder to shoulder, and you do not feel the tiny gravitational attraction between your bodies. Two people still pull on each other gravitationally in the same way the Earth pulls on the moon, just unimaginably absurdly weaker. That difference matters, because it means gravity is not just another force in the lineup. It doesn't behave like the forces that dominate your everyday sensory world. It's everywhere. It shapes everything on large scales, and yet it can be astonishingly gentle at human scales. So, we've already learned something subtle. The force story is a simplification. It captures the effect. It doesn't explain the nature. And that is exactly where the deeper picture begins. But before we go there, it helps to notice another trap, one that feels even more personal. When you think of gravity, you probably think of the sensation of weight. That heavy feeling in the body, the sense that your head is stacked on your neck, your torso pressed downward, your feet planted. Even if you're lying down, you still feel the Earth holding you. There is pressure somewhere, your back against the mattress, your shoulders against the pillow. That sensation becomes proof. It feels like direct evidence that a force is pulling you into the Earth. Yet that sensation, weight, is not as straightforward as it seems, because weight is not simply gravity acting on you. Weight is what you feel when something prevents you from moving freely. That idea sounds backwards at first, but it's one of the most important flips in the entire story, and you can glimpse it without equations. Imagine a moment of true freefall. Not the safe kind on a trampoline, but the pure idea. You and everything around you falling together with nothing pushing back. In that state, you would stop feeling your own weight. Not because gravity disappeared, but because nothing would be resisting the motion gravity is giving you. This is why astronauts float in orbit. They are not beyond gravity. Gravity is still there, strong enough to hold them in a continuous fall around the Earth. They float because everything is falling together, and there is no floor pushing up against their feet. So, the sensation you call weight is a kind of contact sensation. It's the floor pressing on you, the chair supporting you, the ground refusing to let your body follow its natural path. That's a quiet clue that gravity is not exactly what it seems. Because the strongest, most personal evidence of gravity, the feeling in your body, turns out to be evidence of something else: resistance, support, constraint. And once you accept that, even gently, the force picture starts to wobble. Another reason the force picture is so sticky is that it fits our instincts about down. Down feels absolute, but down is not a universal direction. Down is local. It means toward the center of the nearest massive body. If you could travel to the other side of the Earth, down would point the opposite way, yet everyone there would feel perfectly upright. The concept works because you're embedded in a spherical gravitational environment, and your body interprets it as a fixed direction. So, down is not a cosmic instruction. It's a local feature of where you are. And once you start thinking in terms of local features, you're already inching toward the geometry view, whether you realize it or not. Because geometry is the study of shape, and shape is about relationships, how distances and directions behave depending on where you are. Now, in the force picture, we still tend to imagine gravity as something like a field, an invisible presence filling space, pulling objects toward mass. That's a more mature version of the basic idea, and it's closer to how physics actually treats forces in general. But even there, gravity remains a strange member of the family. It doesn't have a clear source the way electric forces do. Electricity comes with positive and negative charges. You can screen it, cancel it, balance it. Gravity has only one sign. Everything attracts. There is no negative mass sitting around to cancel Earth's pull in your bedroom. And because it cannot be screened, gravity ends up shaping the entire architecture of the universe on large scales. It's the reason matter clumps into stars. It's the reason galaxies form. It's the reason the universe has structure at all. Yet it's so weak between small objects that you can defeat the entire gravitational pull of a paperclip with a small fridge magnet. That combination, cosmically dominant, locally whisper quiet, should make you suspicious avoidably, in the same way you'd become suspicious of a story that explains everything while also feeling strangely intangible. So, what are we really saying tonight? Not that what you learned was wrong, it's more delicate than that. The force picture is like a map with the right streets but the wrong scale. It gets you where you need to go until you try to navigate something bigger than a neighborhood. It's a model that works in the regime your body lives in, a model that makes predictions and keeps you safe and lets engineers build bridges and send rockets and land probes. But it leaves out the deeper reason gravity behaves the way it does. It leaves out what gravity is, beyond being a number you plug into equations. And that missing what it is becomes impossible to ignore once you start noticing the cracks where intuition fails. Why does gravity treat all objects the same way, regardless of what they're made of? A feather and a hammer fall together in a vacuum. Why does light respond to gravity at all if light has no mass in the usual sense? Why does time behave oddly near massive objects? Why does the universe allow a single phenomenon to link falling, orbiting, and the ticking of clocks? Those questions don't sound like questions about a simple pull. They sound like questions about the stage itself, about the structure of space and time. And that is the point of this section, to gently set the trap for the old picture so the new one can arrive without force, without conflict, without feeling like a sudden twist thrown in for drama. Tonight we are replacing the picture in your head, not with something louder or more complicated, but with something strangely calmer. A picture where falling is not a tug but a path, where orbiting is not a balance of forces but a natural motion, where gravity is less like a hand reaching out and more like the shape of the world you're moving through. And once that picture settles, you begin to understand why the best description of gravity doesn't start with a force at all. It starts with the geometry of reality itself. There's a reason Newton's gravity feels so satisfying. It doesn't ask you to change the way you see the world. It simply gives your intuition a set of numbers. You already believe that things fall. You already believe the moon stays near Earth. Newton arrives and says calmly, almost modestly, yes. And the same rule explains both. Before Newton, people had pieces. Falling apples here, wandering planets up there, different stories for different realms. Newton's genius was to connect the ceiling and the floor with one quiet thread. He imagined that the same influence that brings a stone back to the ground also reaches all the way out to the moon, not as poetry, as a precise, testable claim. And once you accept that idea, the world becomes strangely unified. A stone falls because Earth pulls it. The moon doesn't crash because it's already moving sideways, fast enough that as it falls, it keeps missing the Earth. It keeps falling around the planet. That single picture, falling as orbit, may be one of the most powerful mental images ever drawn in science. Not because it's complicated, but because it's simple in the right way. Now, Newton didn't speak in the modern language of space-time and curvature. He didn't need to. He gave us a rule, a relationship, a dependable machine. The rule is famous, but it's worth letting it settle gently, without rushing past it. Every mass attracts every other mass. The strength of that attraction grows when the masses are larger, and it weakens as the distance increases, specifically with the square of the distance. That square matters. It means if you double your distance from something, the gravitational pull becomes 4 times weaker. If you triple the distance, it becomes 9 times weaker. It fades quickly. And yet, despite fading quickly, it never becomes truly zero. It reaches out. Always. Everywhere. It's the kind of law that feels like it was written by the universe itself. Elegant, spare, and strangely patient. You can feel the meaning of it with a quiet, ordinary comparison. Earth pulls on you with enormous strength, because Earth is enormous and close. A pencil across the room pulls on you too. The law says it must. But the pencil is tiny, and the distance is comparatively large, so the pull is absurdly small. So small you'll never notice it. That's not a failure of gravity, that's a revelation about scale. Gravity is real at every distance, but it only becomes obvious when at least one of the masses becomes enormous. Planets, moons, stars. Which means Newton's law was, from the beginning, a law designed for the cosmos. Even when you use it in a classroom to explain a falling ball, the law is whispering about the solar system. That's one reason Newton's gravity held the world for so long. It is unbelievably useful. You can use it to compute how hard you must throw something to make it arc and return. You can use it to predict where a planet will be months from now. You can use it to understand why comets return, why tides rise, why the moon doesn't drift away like a lost balloon. And there's something else Newton gave us that feels almost more impressive than the law itself. He gave us permission to believe that the universe is consistent, that there aren't separate rules for the heavens and the earth, that a human mind, sitting on a small world, can write down a sentence of mathematics and have it still be true near Saturn. When you think about it that way, you can understand why Newton's gravity wasn't just accepted, it was trusted. It felt like a miracle that kept working. But tonight's question is not whether Newton was right. He was right, in the way a map can be right. The question is whether Newton's picture is the whole story. Because Newton's picture is, at heart, a force picture. 2 objects reach across empty space and pull on each other. And that idea, action across emptiness, has always carried a faint discomfort. It worked, so people tolerated the discomfort. But the discomfort never fully went away. Even Newton himself was uneasy about the notion of a force acting at a distance with no physical mechanism in between. He could write the math, he could show you the predictions, but he couldn't tell you what gravity was in the deepest sense. He gave you the how much, not the what is it really. And for a long time, that was enough. Because the universe, in most situations, is kind. It lets Newton's law be almost perfectly correct. If you stay in weak gravitational fields, around planets and normal stars, Newton's predictions are stunningly accurate. But there is a second reason the Newtonian story holds our intuition so strongly. It matches the way we feel. If gravity is a force, then it makes sense that you feel it. You feel heavy. You feel pressed downward. You feel the constant insistence of the planet. So your body becomes evidence. But the deeper you look, the stranger that feeling becomes. Consider what gravity is compared to other forces we know. If you bring a magnet near a piece of iron, the pull is immediate and dramatic. If you rub a balloon on your hair and bring it near a wall, you can see static electricity in action with almost comic clarity. Those forces can be strong enough that a small object in your hand can compete with the entire Earth's gravity over a short distance. A magnet can lift metal upward against the planet. Static can pull light objects sideways. Gravity doesn't do that. Gravity is, compared to the electromagnetic force, astonishingly weak. So weak that when you deal with small masses, apples, pencils, people, gravity is nearly invisible as an interaction between objects. You can stand next to another person, and you are, in principle, pulling on each other gravitationally. But it is so tiny that no part of your nervous system evolved to notice it. No muscle in your body responds to it. No sense organ reports it. And yet the same weak force is responsible for the architecture of the universe. It holds galaxies together. It organizes star systems. It sculpts the paths of planets. It turns clouds into suns. So, gravity is both the weakest familiar force and the most dominant force on the largest scales. That contrast is important because it tells you something about how Newton's model is being used. Newton's gravity is a perfectly tuned tool for large-scale, slow-motion situations. It's a rule that becomes powerful when you add enormous mass and enormous distance. But the force picture starts to wobble when you ask a simple question. If gravity is just another force like magnetism, why does it behave so differently? Why is there no way to shield it? Why does it affect everything with mass in the same way? Why does it seem to care about energy too, like light, when light isn't a chunk of matter moving through space? Newton's law doesn't answer those questions. It doesn't claim to. It says, given two masses and a distance, here is the pull. And because it predicts so much, it feels like a complete explanation. But prediction and explanation are not the same thing. A calendar can predict the seasons. It doesn't explain why the planet tilts. So let's slow down and look at what Newton's gravity actually commits us to. In Newton's world, space is a fixed stage. Time is a steady clock. Objects move through space as time passes, and forces act on them, changing their motion. That's the classical worldview in a nutshell. Stage, clock, actors, forces. Gravity, in that worldview, is one force among others, special in scope, but not in kind. And it's a beautiful worldview because it feels stable. It feels like something you can build a civilization on. In fact, we did. But then a small, quiet detail starts to feel more and more unsettling the more you stare at it. Gravity doesn't just pull objects. It gives you a sense of down. It defines what rest means. It changes what straight means in practical navigation. It organizes how things want to move, even when nothing seems to be touching them. And most strangely, it treats all objects the same in free fall. If gravity is a force, why doesn't it accelerate different objects differently based on their internal composition? Electric forces do, magnetic forces do, friction certainly does. But gravity in a vacuum is indifferent. This indifference is not a minor curiosity. It is the seed of the later revolution. Because when a phenomenon treats all objects the same way, it begins to look less like a force applied to the object, and more like a property of the environment the object is moving through. Like a current in water, a current doesn't care whether you are holding a rock or a leaf. It carries both. The difference is in how other forces interact: drag, buoyancy, shape. But the current itself is not choosing. Gravity has a similar flavor. It doesn't ask what you are made of. It asks where you are. Now, there is another gentle way to see the limit of the Newton picture without getting technical. Newton's law tells you the strength of gravity between two objects at a given distance. But it doesn't tell you how quickly changes in gravity happen. If the sun were to suddenly vanish, just as a thought experiment, would Earth instantly fly off its orbit? Or would something propagate outward at a finite speed? In Newton's original framework, the force is simply there. The law is instantaneous. The pull depends on the distance right now, as if the universe updates itself everywhere at once. That's not how nature usually behaves. Information takes time to travel, signals propagate, and once you begin to care about the speed at which influence is spread, you start to sense that Newton's gravity, while accurate, may be an approximation of something deeper, something compatible with a universe where nothing updates instantly. And none of this is meant to diminish Newton. If anything, it elevates him, because his gravity is the most successful first picture we have ever had. It describes the world with such clarity that it remains the backbone of engineering and spaceflight in many practical settings. Even today, when we send spacecraft across the solar system, we use Newton's gravity as the foundation, then add small corrections when needed. That's the mark of an extraordinary theory. It stays useful even after it's no longer the deepest story. So here's the right way to hold Newton in your mind tonight. Newton gave us the language of orbits and the architecture of prediction. He gave us a universe that could be calculated. He taught us that the same rule shapes apples and moons. But he also left us with a question he could not answer. What is gravity really? Is it a pull across emptiness? Or is it something about space itself? Newton gave us the math. And in a moment, when the first cracks begin to show in the predictions, we'll see why the universe eventually demanded more than math. It demanded a new picture. For a long time, Newton's gravity didn't just work. It worked so well that it changed what people thought an explanation was supposed to feel like. Because once you have a rule that can tell you where Mars will be months from now, or when an eclipse will arrive, you begin to trust that rule the way you trust a sturdy bridge. You stop thinking of it as an idea. You treat it like part of the world. That's the quiet power of Newton's triumphs. They weren't loud. They were dependable, and dependability is the most persuasive kind of magic. Newton's law gave the universe a kind of clockwork dignity. If you knew the masses and distances, you could calculate the pull. If you knew the pull, you could calculate the motion. And if you could calculate the motion, you could begin to believe that the cosmos, vast, cold, indifferent, was still legible. You can see why that would be intoxicating, because before that, the sky had always carried a hint of mystery you couldn't touch. The stars were not just far away, they were separate, beyond the ordinary. Newton erased that psychological border. He made the heavens feel nearby, not in distance but in understandability, and the universe rewarded that confidence immediately. Start with the most obvious triumph, the planets. To the naked eye, planets do strange things. They wander, they loop, they stall and reverse. Ancient astronomers built elaborate systems to match those movements, clever, intricate machinery of circles on circles. Newton didn't need circles on circles. He needed one simple thing, a central pull and an object moving sideways. Once you combine those two, you don't get a perfect circle. You get a family of shapes, ellipses, curves, paths that can stretch and tilt and change. In other words, you get something flexible enough to match the real sky. And what's more important than matching the shape is matching the pattern. When a planet is farther from the sun, it moves more slowly. When it's closer, it speeds up. That's not a poetic statement. It's a measurable fact you can notice even without instruments. Mars lingers, Jupiter drifts, Mercury whips around quickly near the sun. Newton's law makes that slowness and speed feel inevitable. Farther away means less gravitational pull. Less pull means less curvature of the path, and less speed needed to maintain the orbit. So the outer planets take their time. The inner planets hurry. The universe stops behaving like a puzzle and starts behaving like a consequence. And then there are tides, one of the most intimate cosmic phenomena, because the ocean is in your backyard, and yet its rhythm is written by the moon. Tides seem, at first, like a local quirk, wind and waves and coastline. But Newton's gravity can explain why there are two bulges, why the timing drifts, why the moon's position matters, why the sun can amplify or soften the effect depending on alignment. Even if you don't track every detail, the emotional effect is powerful. The same law that governs the moon's orbit also lifts the sea. So Newton doesn't just explain the sky. He explains your shoreline. And once a theory starts explaining both the unreachable and the familiar, you begin to treat it as reality itself. But perhaps the most persuasive triumph is not a planet or an ocean. It's the sheer accuracy of prediction. Newtonian gravity allowed astronomers to produce tables, calendars, ephemerides, precise listings of where planets should be on any given night. It turned the sky from a realm of omens into a realm of schedules. That kind of success doesn't merely impress people, it trains them. It trains them to believe that the universe has a hidden order, and that mathematics is a way of reading it. This is why Newton's gravity became the default mental picture for generations. Not because people were stubborn, but because the theory kept earning their trust. And then comes one of the most famous demonstrations of that trust paying off, the story of Neptune. In the early 1800s, astronomers noticed something subtle. Uranus, the newly discovered planet, wasn't moving exactly as predicted. Not wildly wrong. Not enough to throw out the theory, just not quite obedient. A tiny mismatch spread over years. This is the kind of mismatch you could easily dismiss. Measurement errors, bad instruments, a miscalculated mass somewhere. The sky is complicated. But the Newtonian worldview had a certain pride by then. It had become normal to assume that the math was right, and therefore the universe must contain whatever was needed to make the math work. So instead of abandoning Newton, scientists leaned into him. They used the deviations in Uranus's orbit like fingerprints, like the shape of a shadow. If something unseen was tugging on Uranus, then Newton's law could tell you where that unseen thing should be. And that is exactly what happened. Two mathematicians, working independently, predicted the position of a new planet based purely on gravitational effects. Astronomers pointed their telescopes at the calculated spot. And there it was, a planet no one had ever seen, quietly sitting in the darkness, revealed not by direct observation first, but by the way it bent the motion of another world. That is a triumph so clean it almost feels scripted. The universe did something that looked like a demonstration, as if it were saying, yes, your law is real, keep going. It's hard to overstate what that did to the scientific imagination. Because Neptune wasn't just a new planet. Neptune was a proof of method. A proof that you could infer invisible things from visible consequences. A proof that gravity wasn't merely descriptive, it was diagnostic. And that's exactly the kind of success that makes a theory feel final. When a theory starts finding objects for you, you stop asking it to justify itself. You start asking it to find more. Newton's gravity also made sense of comets, those long arc visitors that appear like myths, then vanish for decades, then return. Once you treat a comet as a body obeying the same gravitational law as everything else, its path becomes a long, thin orbit, an ellipse stretched into a near line. A periodic return becomes a consequence of geometry and gravity, not a mystery. Again, the emotional pattern repeats. What was once eerie becomes ordinary, and the ordinary becomes calming. That's why this material, when told gently, fits a sleep channel so well. Not because it's boring, but because it takes chaos and turns it into structure. Now add another quiet triumph, the idea that the same law works on Earth too. If you throw a ball, its path curves. If you fire a cannon, it goes farther. If you fire it fast enough, this is the classic Newtonian thought, you could, in principle, have it curve around Earth and never land. An orbit is just a fall with enough sideways speed. That picture takes something you felt in your hand throwing and connects it to something you've only imagined, satellites. It makes spaceflight feel like an extension of playground physics. And in many ways it is. So by the time we arrive in the modern era, rockets, satellites, lunar missions, we're still living inside Newton's triumph, even if we don't realize it. A huge amount of practical navigation and engineering still leans on Newtonian gravity as the first approximation, because it is so effective. And that fact matters for our story, because it explains why the next shift was so hard. When a model is merely kind of right, it's easy to replace. You feel no loyalty? When a model is spectacularly right, when it predicts the sky, explains the ocean, finds planets, and helps you aim spacecraft, replacing it feels almost disrespectful. It feels like replacing something sacred, which is why the real turning point could never be a dramatic failure. It had to be something subtler. It had to be a crack, a tiny mismatch that refused to be ignored. And Newton's triumphs made that crack more painful, not less. Because if the theory is mostly right, then any deviation becomes deeply suspicious, not of the theory's usefulness, but of its completeness. A small discrepancy becomes a kind of philosophical itch, the kind you can live with for a while, until you can't. So, when we say Newton ruled for about 2 centuries, we don't mean people were simply repeating an old idea. We mean the universe kept agreeing with him, over and over, across the solar system, across the tides, across the comets, across the discovery of an unseen planet. And if you were living in that era with that evidence, you would have believed the story was finished too. You would have thought, we have gravity, we understand it, it's a force, it pulls, it follows a clean inverse square law, it predicts everything that matters. And then, very patiently, the universe placed one stubborn detail on the table, not to humiliate Newton, but to invite the next idea, a detail so small that you could measure it in arc seconds, a detail that lived in the orbit of the planet closest to the sun, a detail that would not go away, no matter how carefully you did the math. And that's where the mood changes, quietly, almost politely, from triumph to discomfort. There's a particular kind of problem that only shows up after you've been right for a very long time. Not the loud kind of wrong, where everything collapses and you have to start over. The quiet kind. The kind that hides inside success, like a hairline fracture in a strong piece of glass. You can't see it from a distance. You only notice it when you lean in close, and the light hits it just right. That's what happened to Newton's gravity. For 2 centuries, the universe kept saying yes. Yes to the planets, yes to the tides, yes to comets returning on schedule, yes to invisible Neptune revealed by mathematics alone. So, when a small disagreement appeared, it didn't feel like a normal error. It felt personal. Because if you believe your theory is the language of nature, then nature isn't supposed to stutter. The crack arrived in a place that seems almost poetic, the innermost planet, Mercury, the one that lives nearest to the sun, deep in the bright, intense region where gravity is strongest, where every orbit is tight and fast and constantly tugged by everything else. At first glance, Mercury looks obedient. It goes around the sun just like Newton said it should. But astronomers don't just track a planet's position. They track the shape of its orbit too. They track how that ellipse sits in space, where the closest point to the sun is, where the farthest point is, and how that whole oval slowly rotates over time. That slow rotation is called precession, and it happens for a normal reason. The solar system isn't a clean 2-body problem. Jupiter pulls a little, Venus pulls a little, Earth pulls a little. Even the sun isn't a perfectly smooth, isolated point. The result is that Mercury's orbit doesn't repeat the exact same ellipse forever. The ellipse itself slowly swivels, like a hula hoop that turns a tiny amount each lap. Newton's math could account for that, and for a while, it looked like it did. But as measurements improved, more careful observations, better telescopes, better math, something stubborn remained, a leftover, a remainder that refused to be explained away. It wasn't huge, it wasn't dramatic, it was almost insultingly small, a mismatch of about 43 arc seconds per century. An arc second is a tiny angle, so small that it's hard to picture without a comparison. Imagine a single degree in the sky, now cut it into 60 arc minutes. Now cut one of those arc minutes into 60 arc seconds. That last sliver is an arc second. 43 of those, spread over 100 years, is the kind of difference you could miss if you weren't obsessively careful. But science is built on obsessive care. And once you've seen a discrepancy like that, you can't unsee it. The discomfort wasn't that Mercury behaved strangely. The discomfort was that Mercury behaved almost perfectly. Almost. That almost is dangerous, because it invites a certain kind of thinking. If the theory is right, then the universe must contain something extra that we haven't accounted for. So, scientists did what successful science always does first. They tried to fix the model without changing the model. They searched for hidden influences, hidden masses, hidden bodies, anything that could supply an extra nudge, something that would twist Mercury's ellipse just a little more, precisely enough to account for those missing arc seconds. And this is where the story takes on a strange, almost dreamlike quality, because it reveals how human the scientific process is, even when it's working. Instead of throwing out Newton, people went hunting for a new planet. Not Neptune, out in the cold. Something closer in, something inward of Mercury, closer to the sun than anyone had ever seen. They even gave it a name, Vulcan. The name itself feels like an artifact of that era. The Roman god of fire, a planet imagined to live in the blazing furnace near the sun. The logic was clean. If Uranus's orbit had led to Neptune, then Mercury's orbit might lead to Vulcan. A hidden planet could tug on Mercury and create the extra precession. It would be the same kind of triumph again. Gravity diagnosing an invisible world. So people looked. They watched for tiny dots crossing the sun's face. They searched in the glare. They reported sightings, sometimes sincerely, sometimes mistakenly, because looking near the sun is brutally difficult. The atmosphere shimmers, instruments distort, human attention fills in gaps. For a while, Vulcan became one of those ideas that lives in the in-between space. Not fully real, not fully dead. It was a solution that felt like it should exist. A neat patch, a satisfying answer. And those are the most seductive answers, because they allow you to stay asleep inside your old picture of reality. But Vulcan never solidified into fact. No consistent orbit, no repeated reliable observation, no confirmation that held up under scrutiny. The theory needed a planet, but the sky wouldn't provide one. So the next instinct was to adjust Newton's law itself, just a little. Could the inverse square dependence be slightly different at small distances? Could there be a subtle correction that only matters close to the sun? People tried, they proposed modifications, they tested, but those fixes tended to break other things. And that's the cruel beauty of a theory that has earned trust across the solar system. It's tightly constrained. You can't casually tweak it without consequences. Mercury was teaching an uncomfortable lesson. When a theory is broadly successful, a small anomaly isn't an invitation to decorate it with extra knobs. It's a warning that your mental picture might be missing something deeper. Still, for decades, that anomaly just sat there, a small thorn in an otherwise smooth fabric. And what's fascinating, especially in a calm nighttime way, is how long it took for the world to accept that the crack wasn't going away. Because 43 arc seconds per century is not the kind of thing that interrupts daily life. It doesn't change the weather. It doesn't change the tide schedule. It doesn't stop ships from navigating. It doesn't stop planets from appearing where you expect them to appear. So you can live with it. You can say, we'll figure it out eventually. But science doesn't forget. It keeps a ledger. And Mercury's ledger entry stayed open. This is one of those moments where you can almost feel history holding its breath, because the problem wasn't Mercury. The problem was the meaning of gravity. Newton's framework, as beautiful as it is, carries a silent assumption. Gravity is a force that reaches across space instantly, acting between masses no matter how far apart they are. And for ordinary life, that assumption works so well that it feels like common sense. But when you push into extremes, high speeds, strong gravity, very precise measurements, common sense starts to fray. Mercury lives in an extreme neighborhood. Not the most extreme, but enough to reveal cracks that the outer planets wouldn't notice. So Mercury became a kind of stress test for the universe's operating system. And it failed in the smallest, most maddening way. Now, it's important to hold on to the mood of this moment because it's easy, in hindsight, to tell the story like it was obvious, as if everyone should have known Einstein was coming. But at the time, the anomaly didn't feel like a door into a new universe. It felt like a stubborn accounting error. And that's why it's so persuasive, because this is what real scientific revolutions often look like from the inside. Not fireworks, but paperwork. Not drama, but lingering discomfort. A mismatch so small that only the most careful minds bother to care about it, until the day someone discovers that the mismatch is the clue. Mercury's extra precession wasn't a random flaw. It was a signature, a hint that the geometry of space and time might not be as rigid as people assumed, a hint that the sun's presence does more than pull, it reshapes the stage itself. And when the right idea finally arrived, it didn't solve Mercury by adding a new planet or adjusting a constant. It solved Mercury by changing what gravity is. That's what makes this crack so important. It wasn't a problem at the edge of knowledge, in some exotic corner. It was a problem in the heart of the solar system, inside a theory that had already become the backbone of reality. It was the universe, gently and persistently telling us, you have the right math, but you're holding the wrong picture in your head. And once you accept that possibility, once you let yourself consider that gravity might not be a pulling force at all, Mercury stops being an embarrassment. It becomes the first quiet proof that a deeper description is waiting. A description where orbits are not being yanked into curves, but are tracing the straightest paths they can through a space that is no longer perfectly flat. A description where the sun doesn't just attract, it bends. And the smallness of the crack is the final, calming detail. Because it means the old picture wasn't useless. It was almost exactly right. It just wasn't the whole story. And tonight, that's the gentle shift we're making. Away from gravity as an invisible hand reaching out, and toward gravity as the shape of the world itself. The crack in Mercury's orbit had a strange effect on the scientific imagination. It didn't scream that Newton was wrong. It whispered that Newton might be incomplete. And that whisper mattered, because Newton's gravity wasn't just a convenient idea. It was a kind of mental furniture. It was how people pictured the universe doing its work. Bodies tugging on bodies across empty space by an invisible pull. So if Mercury didn't quite agree, you could try to patch the story. You could add a hidden planet. You could adjust a constant. You could pretend the mismatch would dissolve with better data. But at some point, the stubbornness of the mismatch begins to change its meaning. It stops being an error. It becomes a clue. And in the early 20th century, the clue didn't lead to a new object in space. It led to a new idea about space itself. Because the deepest, quietest assumption inside the old picture was this: space is just a stage, a passive backdrop, a flat, rigid grid where events take place and forces act upon objects moving through it. Newton's law could be written on paper and used to guide ships, predict eclipses, and map planets. But the law didn't tell you what gravity is. It told you what gravity does. It gave the choreography, not the stage directions. Einstein's move was to turn the stage into part of the story, not as a poetic metaphor, as a physical thing. And the way into that idea begins with something we normally treat as separate: space and time. In everyday life, space feels like the room you move through. Time feels like the clock that keeps going no matter what you do. You can walk north or south, left or right, up or down, but you can't walk to tomorrow. So the mind naturally puts them in different categories. Yet, physics kept bumping into situations where that separation started to look less like a truth and more like a habit. When speeds get high, when light becomes the yardstick, space and time stop behaving like independent containers. They start behaving like two aspects of one structure, a single woven fabric. It helps to think about how you locate an event in your life. If someone says, "Where did you meet your friend?" you might say, "At a coffee shop." But that answer isn't complete unless you also say when. Because the coffee shop contains many different moments. To describe a real event, you need both a place and a time. A 4-number address, not a 3-number one. Einstein took that seriously. He treated every event as something with a space-time location, an address in a 4-dimensional world. And this wasn't just bookkeeping. It was a hint about what reality is made of at the deepest level, not separate space plus separate time, but space-time as one unified arena. Now, if space-time is an arena, you might still imagine it as perfectly flat, a smooth, unchanging geometry, like an infinite grid stretching in all directions. That's what most people assumed. Then Einstein asked a question that sounds almost too simple. If mass and energy can move objects, why couldn't they affect the arena those objects move through? If space-time is real enough to define distances and durations, real enough to tell light how to travel and clocks how to tick, Why wouldn't it be something that can change shape? That is the core of the shift. Gravity is not a mysterious pulling force that acts inside a fixed space. Gravity is the behavior of space-time itself. Mass and energy do not merely sit in space-time, they shape it. And when space-time is shaped, motion changes. Not because something reaches out and yanks you, but because the straight lines you thought you were following are no longer straight in the old, flat sense. This is where the word curvature enters. In everyday language, curvature sounds like bending into some higher direction, like a sheet being pushed downward, like a surface that sags. And that's why people reach for the famous rubber sheet analogy. You've probably seen it, a stretched fabric, a heavy ball placed in the center, and smaller marbles rolling around, spiraling inward or orbiting. It's not a useless image, it captures one important intuition. Mass changes the geometry, and other things respond to that change, but it can also mislead. Because the rubber sheet needs Earth's gravity to make the heavy ball sink. So if you take it too literally, you end up in a circular explanation. Gravity causes the dip that explains gravity. And even more importantly, the sheet is a two-dimensional surface sagging into a third dimension. Real space-time curvature doesn't require an outside direction to bend into. It can be curved intrinsically, meaning its geometry is different on the inside, without needing to be embedded in a higher space you can point to. So, we can keep the rubber sheet as a gentle guide, as long as we treat it like a shadow on the wall. Helpful, but not the real object. The real object is geometry. And the most powerful calming part of geometry is that it turns mysterious pulling into natural motion. Because once you accept that space-time can be curved, you can define what it means to move without being pushed. In flat space, the straightest possible path is a straight line. In curved space, the straightest possible path is called a geodesic. A geodesic is not straight in the sense of a ruler line on a sheet of paper. It's straight in the deeper sense. It's the path with no sideways turning, the path that locally feels like the simplest, most direct route. On a globe, geodesics are great circles. If an airplane flies from one continent to another, the route often looks curved on a flat map. But on the sphere, it's the closest thing to straight. The curvature is not a mistake of the airplane. It's a property of the surface. Einstein's idea was that free motion through space-time is like that. Objects aren't being pulled into curves. They are following the straightest paths available in a geometry that isn't flat. And suddenly gravity starts to look less like a force and more like a kind of guidance system built into reality itself. A planet orbiting the sun is not a stone being pulled by a distant hand. It is a body moving forward through a space-time shaped by the sun's mass and energy in a way that makes straightest look like an orbit. And the elegance of that picture is that it doesn't just decorate Newton's law. It explains why Newton's law worked as well as it did. Because in the limit of weak gravity and slow speeds, like most of daily life, curved space-time behaves almost like flat space-time, and geodesics behave almost like Newtonian trajectories. And Newton becomes a superb approximation, a simplified map that is accurate in the regions where most humans live. But once you go closer to the sun, where the curvature is stronger, you begin to see the edges of the map. That is where Mercury comes back into the story. In Newton's picture, Mercury's orbit precesses because other planets tug on it, and because the system isn't perfectly isolated. Those effects are real, and they account for most of the precession. But Einstein's geometry adds a new ingredient. The sun's gravity is not merely an attraction in space. It is a change in the structure of space-time around the sun. The straightest paths around the sun are subtly different from the ones Newton would predict. That subtle difference is tiny. And that's the point. It's exactly the kind of difference that would appear as a small leftover, like 43 arc seconds per century. So, what looked like an annoying accounting error becomes a signature of curvature, a quiet fingerprint, a confirmation that the arena itself is participating. Now, it's tempting to imagine Einstein just declaring this new picture, as if it appeared fully formed. But the real beauty of the move is how it connects to something you can feel, even if you've never done a physics calculation. The relationship between motion and weight. Imagine you are standing still on the ground. You feel heavy, you feel pressed into the floor, you feel that the floor is holding you up. In the old picture, you might say, gravity pulls you down, the floor pushes you up, and you are at rest. Einstein reframed the feeling. He suggested that the most natural state in gravity is not standing still on the ground. The most natural state is freefall. Freefall is what you get when nothing resists your motion through space-time, when you simply follow a geodesic. And the strange twist is that the feeling we call weight is not gravity acting on you directly. It is the floor preventing you from following the geodesic you would otherwise follow. In other words, gravity doesn't feel like falling. Gravity feels like being held back from falling. That idea, often tied to what's called the equivalence principle, will become its own deep, soothing story later in the video. But even here, it shows why Einstein's move is so powerful. It takes a force and replaces it with geometry plus motion. You don't need a pulling agent. You need a curved arena and an object that moves naturally within it. And once you think that way, a lot of strange extra features of gravity begin to look inevitable. For example, if space-time is geometry, and geometry defines both distances and durations, then gravity shouldn't only affect how things move through space. It should affect how time flows. In the Newtonian worldview, time is a universal metronome, one cosmic clock, the same tick everywhere. But in Einstein's worldview, time is part of the fabric. If the fabric is warped, the ticking can differ from place to place. That sounds almost mystical when you first hear it. But it's actually the opposite. It's brutally literal. Clocks don't live outside space-time. They live inside it. Their ticking is a physical process unfolding along a path through space-time. Change the geometry, and you change what 1 second means along different paths. This is why gravity, in Einstein's description, naturally leads to gravitational time dilation, the idea that time can run at different rates in different gravitational conditions. And it's why light too should respond. Because if space-time tells matter how to move, it also tells light how to travel. Light follows geodesics as well, special ones but still guided by geometry. So, light can bend near massive objects, not because it has weight like a rock, but because the straightest route in curved space-time is not the straight line you would draw on a flat diagram. Notice what's happening. One conceptual shift, gravity as geometry, doesn't just fix Mercury. It unifies a whole constellation of weirdness into a single, calm framework. Orbits as natural paths. Weight as resistance to natural paths. Time behaving differently in gravity. Light responding to gravity. The possibility that extreme gravity produces extreme geometry. And that last one is where the story quietly points toward its most dramatic objects, black holes. If mass curves space-time, then concentrating mass into smaller and smaller regions increases curvature. At some point, the geometry could become so steep that the geodesics you can follow all tilt inward. Not because something is pulling harder, like turning up the volume on a force, but because the shape of space-time becomes so distorted that forward and inward begin to align. That's later. For now, stay with the elegance of the move. Einstein didn't improve Newton by polishing the force. He changed the ontology of gravity. He replaced an action at a distance pull with a local geometric rule. Locally, in a small patch of space-time, physics looks normal. You can approximate it as flat. You can do your everyday logic. You can throw a ball and see a smooth arc. But globally, the patchwork can curve and flex in response to mass and energy. And that is the key reason the idea feels both unsettling and comforting. Unsettling because it means space and time are not the cold, empty nothing we casually imagine. Comforting because it means gravity is not a mysterious hand reaching across the void. It is simply the shape of the world and the way things move when no one is pushing them sideways. That, in the end, is why the Mercury crack matters so much. It wasn't asking for a new planet. It was asking for a new picture. A picture where the universe doesn't need invisible ropes. It needs geometry. And once you let that picture settle in your mind, a sentence that once sounded like a provocation starts to sound like a description. Objects aren't pulled. They follow the contours of space-time. Picture this as simply as possible. You're standing on the floor. Nothing dramatic is happening. No rocket launches, no spacewalks. Just you, and the quiet fact that you feel your own weight. That feeling is so familiar that it becomes invisible. It's the background sensation of being alive on Earth, the gentle pressure in your feet, the way a chair pushes back, the way your body seems to settle into whatever is holding you. We call that feeling gravity. And that's the first trap, because in Einstein's picture, gravity is not the thing you feel when you're standing still. Gravity is what you experience when you're not being held back. Gravity is what happens when you're allowed to move freely. In other words, the most natural motion in a gravitational field is not rest. It is freefall. That sounds backwards at first, because we've trained ourselves to think gravity pulls downward, so falling must be what gravity does, and standing still must be not moving. But the deeper story is stranger and simpler. When you're falling freely, you are not being forced into anything. You are doing the most effortless thing possible. You are following the straightest path available in curved space-time. And when you are standing still on the ground, you are being forced away from that path. The floor is pushing you upward. The sensation you call weight is not gravity pulling you down. It is the world pushing you up. If you let that idea sit for a moment, it changes the entire feeling of gravity, because it turns weight from a cosmic pull into a local resistance. It turns down into geometry, and it turns the ground beneath you into an active participant in your experience of reality. You can see the difference in the place where people assume gravity disappears, low Earth orbit. The International Space Station circles Earth at roughly 400 kilometers up. That sounds high. It's above the atmosphere most of us think of as the sky. So the intuition says it must be far enough that gravity is almost gone, but it isn't. Earth's gravity at that height is still the vast majority of what it is at the surface, something like 90%, give or take. So why do astronauts float? Because floating is not the absence of gravity. Floating is what happens when everything around you is falling together. The station is moving sideways so fast that as it falls, the Earth curves away beneath it. It is in continuous freefall, but it keeps missing the ground. And the astronauts inside are also in freefall. They aren't being held up by a floor. They aren't being supported by a chair the way you are right now. So they don't feel weight. Not because gravity's gone, but because nothing is resisting their natural motion. Now, here is where Einstein does something quietly brilliant. He makes a claim that sounds almost like a magic trick, but it isn't. He says, in a small enough region of space and time, freefall feels exactly like being far away from gravity entirely. If you were inside a sealed elevator and the cables snapped, and you and the elevator began to fall together, you would feel that weightless floating. Your stomach might flip for a moment, but then, if the fall were smooth enough, your body would feel strangely calm. A coin you let go of would hover beside you. A drop of water would hang like a small shining bead. Everything would drift as if gravity had been turned off. And inside that elevator, you would not be able to tell, by any local experiment, whether you were falling in a gravitational field or drifting in deep space. That is the equivalence principle in its most gentle form. Locally, being in freefall is equivalent to being in an inertial frame with no gravity. It's not that gravity doesn't exist. It's that in freefall, gravity becomes part of the background geometry of your motion, and you stop feeling it as a force. Because forces are things you can feel. Pushes, pulls, strains, accelerations relative to your natural motion. Freefall removes that feeling. And now the next step, Einstein's favorite step, is to reverse the scenario. Instead of a falling elevator, imagine a sealed elevator floating far out in space, nowhere near a planet. It's quiet. It's drifting. Now, imagine that elevator begins to accelerate upward, smoothly, steadily, at the same rate that objects accelerate downward near Earth's surface. Inside, you let go of a coin. What happens? The elevator floor rises to meet it. From your perspective inside, the coin falls. It lands. It behaves exactly as if gravity exists. If you pour water, it splashes down. If you stand, you feel pressed into the floor. If you jump, you come back down. And if the acceleration is steady and smooth enough, there is no local experiment you can do that tells you whether you are in a rocket accelerating through empty space or standing still in a gravitational field. Again, not poetic. Physical. This is the equivalence principle in the other direction. A gravitational field and an accelerating frame are locally indistinguishable. And that single idea, simple, almost childlike, becomes a lever strong enough to move the concept of gravity itself. Because if gravity behaves like acceleration, then gravity is not simply a force reaching across space. It is something built into the structure of motion. It is something about the geometry of the paths you naturally follow. And now we can return to the everyday experience of weight with a new definition. Weight is what you feel when you are prevented from following your natural freefall path. You are always trying to follow a geodesic, a straightest possible path through space-time. But the floor interrupts that. It pushes you away from the geodesic you would otherwise take. So, the sensation in your feet is not gravity pulling. It's contact. It's resistance. It's the world telling your body, you don't get to fall right now. That reframing is why Einsteinian gravity can feel so calming once it clicks. It removes the image of an invisible hand dragging you downward. It replaces it with an image of motion that is already happening, quietly, continuously, through the shape of space-time. Freefall becomes the default. Standing still becomes the special case. And once you see it that way, you can start noticing how deeply this idea is hidden inside the modern world. Think about a satellite again. It isn't held up by some anti-gravity trick. It is simply moving along its natural path, with nothing to support it in the ordinary sense. It's not fighting gravity, it's cooperating with it. It's the same with the moon. The moon is imbalanced between pulling and not pulling. It is falling around the Earth in a way that never completes the fall. It's as if the universe has replaced force with path. Now, there is one more subtlety that makes this story even more satisfying. In Newton's picture, gravity is an influence that tells objects how to accelerate. In Einstein's picture, gravity is the geometry that tells objects what counts as straight motion. So, the laws of motion don't need gravity as a separate input. They need geometry. And geometry, in turn, is shaped by mass and energy. That is the trade. Instead of a force field acting on objects, you get a curved arena in which objects move naturally. And the equivalence principle is the hinge that lets you make that trade without losing contact with reality. Because it anchors the abstract idea, curved space-time, to a concrete feeling, the feeling of weight, and the feeling of weightlessness. It says, pay attention to what you can and cannot feel. If you're falling, you don't feel gravity as a force. If you're supported, you do. So, the force is not where you thought it was. It isn't an empty space between you and Earth, like a rope under tension. It's in the interaction between your body and whatever is preventing your body from taking its natural route. That is why astronauts can float while still being deeply in Earth's gravity. That is why the ISS can be surrounded by gravity and still feel weightless. And it is why a rocket in deep space can manufacture gravity simply by accelerating. The universe allows this because the sensation of gravity is, at its core, the sensation of not being in freefall. Now, you might wonder if that's true, if freefall is the natural state, why do we ever talk about gravity as a force at all? Because in everyday life, we live almost entirely in the supported state. We sit in chairs, we sleep in beds, we walk on floors. Our bodies spend most of their time being prevented from freefall. So we build an intuition that gravity is what presses us down. But that intuition is built from the exception, not the rule. And once you recognize that, a few other weird facts begin to feel less weird. For instance, if gravity is geometry, then falling is not a special event. It's simply what happens when you stop interfering. That's why a dropped object accelerates without you doing anything. That's why a planet can orbit without a continuous push. That's why a photon can bend near a massive object without needing to have weight in the old sense. Everything is following the same principle. Motion is natural, geometry guides it. And the role of mass and energy is not to reach out and pull. It is to shape the geometry those motions unfold within. The equivalence principle is also the reason Einstein could predict something that sounds almost impossible, that time itself behaves differently in gravity. Because if gravity and acceleration can be mimicked, then the behavior of clocks in gravity must match the behavior of clocks in accelerating frames. And accelerating frames, once you take relativity seriously, have deep consequences for time. So, the equivalence principle doesn't just explain weight and freefall. It quietly opens the door to gravitational time dilation, to redshift, to the idea that down in gravity is not merely a direction in space, but a direction through a curved structure that includes time as well. But we don't need to rush there. For now, the central surprise is enough. If you remember only one thing from this stretch of the story, let it be this. Freefall is the calm, natural motion. Weight is the interruption. Gravity is not what you feel when you are falling. Gravity is what you infer when you notice that the world keeps having to hold you up. And if you like, you can take that thought back to the simplest scene again. You standing on the floor. Nothing dramatic, just a quiet, constant push rising through your feet. Not from the sky above you, from the ground beneath you. A reminder that the force you think you feel is really contact. And that underneath that contact, the universe is always offering the same effortless path to fall freely along the contours of space-time. There's a quiet detail hidden inside gravity that most people never notice, because it doesn't announce itself with a shove or a pull. It doesn't snap your keys out of your hand, or tilt a glass of water, or make a branch bend. It does something subtler. It changes the tempo of reality, not in a poetic way, in a measurable way, in a way that can be written down, tested, corrected for, and built into the devices you use every day. Gravity doesn't just guide where things go. It also influences how fast now moves. If you've grown up hearing that time is steady, 1 second after another, perfectly uniform, this is the moment where that comfortable picture starts to soften at the edges. Because in Einstein's universe, time is not a universal drumbeat. Time is local. It belongs to the place you're in. And the strength of gravity where you are, meaning the depth of the gravitational well, changes how quickly your clock ticks compared to someone else's. The simplest way to feel the idea without getting lost in equations is to imagine time as something that has to climb. Near a massive object, space-time is shaped in a way that makes up and out a little more expensive, not only for objects moving through space, but for processes unfolding through time. So, deep in a gravitational field, time runs a little more slowly. Higher up, where gravity is weaker, time runs a little more quickly. That sentence sounds like a riddle at first, but it has a clean, calm meaning. It means two identical clocks, separated by height, will not agree forever. The one lower down, closer to the mass, will tick slightly slower. The one higher up will tick slightly faster. No drama, no flashing lights. Just a tiny difference accumulating, quietly, like dust settling on a shelf. And now the obvious question appears. If time can run differently in different places, why doesn't the world feel chaotic? Why don't we notice it? Because on human scales, the effect is small. You don't feel it the way you feel temperature or pressure. Your body doesn't have a built-in alarm that says, time is 0.00000000004% slower here. But physics doesn't care whether you can feel something directly. Physics cares whether it's true. And the truth is that gravity's influence on time has been tested again and again, first as a daring prediction, and later as a practical engineering problem. One of the earliest clean ways to talk about this is to remember the equivalence principle you already set up. If a gravitational field can be mimicked by acceleration, then the time effects you would expect in an accelerating frame should also show up in gravity. Imagine a rocket accelerating up through space. If you send a pulse of light from the floor to the ceiling is moving away from the light as it travels. By the time the light arrives, the ceiling has gained a little speed. From the ceiling's point of view, the arriving light looks slightly shifted, stretched to a lower frequency. That's not because the light got tired. It's because the receiving frame has changed during the travel. Now, replace the accelerating rocket with a gravitational field, and the same logic carries over. Light climbing upward in a gravitational field will be measured as slightly lower in frequency at the top than at the bottom. That shift is called gravitational redshift, and it's one of the most elegant hints that gravity isn't merely a force acting on objects. It's a structure that affects everything moving through space-time, including light itself, and the clocks that measure it. But before we even talk about light, we can stay with something gentler: clocks. What does it mean physically for time to run slower? It means any repeating process, an atom vibrating, a pendulum swinging, a quartz crystal oscillating, will run at a slightly different rate depending on gravitational potential. A second is defined by a certain number of transitions in a particular atom. So, if gravity changes how that atomic process unfolds, gravity changes the realized length of a second at that location. Not because the atom knows gravity exists, but because the geometry of space-time changes what proper time is along that world line. That phrase, proper time, sounds technical, but the idea is simple. Proper time is the time measured by a clock traveling with you, living where you live, moving how you move. Einstein's point is that proper time is what's real for each observer. And proper times can disagree when observers live in different gravitational environments. If this still feels too abstract, it helps to anchor it with a story that feels almost old-fashioned, like a science experiment from a calmer era. In the early 1970s, scientists took atomic clocks so precise they can reveal the universe's tiniest cheats, and put them on airplanes. They flew them around the world. Then they compared them to clocks that stayed on the ground. If the old picture of time were perfectly true, the clocks would match. But they didn't. The moving clocks and the ground clocks diverge by tiny amounts consistent with relativity. Once you accounted for both speed effects, special relativity, and gravity effects, general relativity. Even without memorizing the details of the routes or the exact numbers, the emotional weight of the result is enough. Time is not one global river. Time is a landscape, and motion and gravity decide the slope. Now, let's bring it closer to the present, where the experiments don't require airplanes and headlines. Modern atomic clocks are so sensitive that you don't need a trip around the world to see gravitational time dilation. You can see it by changing altitude by something as ordinary as the height of a person. In one famous demonstration, researchers compared clocks separated by roughly a third of a meter, about the height difference between your head and your feet. And they measured the difference. The effect is incredibly small, but the point is not the size. The point is that the effect exists, and it's exactly what Einstein's picture says it should be. Gravity doesn't just pull, it slows. And if you're listening late at night, letting your mind drift, you can allow that fact to feel both strange and oddly peaceful, because it means the universe is not merely a machine of moving parts. It's a system where even time participates. The deeper you are in gravity, the more expensive time becomes. The higher you go, the more time loosens slightly, like a tight knot relaxing. Now, there is a place where this stops being only a philosophical wonder and becomes a practical necessity. GPS. GPS works by timing. A satellite sends a signal stamped with the time it was transmitted. Your receiver compares the arrival times from multiple satellites and uses those differences to calculate position. This is not sort of timing. This is timing at the level where a few billionths of a second matter. Light travels about 30 centimeters in a single nanosecond. So if your timing is off by 10 nanoseconds, you can be off by about 3 meters. If your timing is off by a microsecond, you can be off by about 300 meters. And if it drifts continuously, the error compounds quickly. Now remember where GPS satellites live. They orbit high above Earth, where gravity is weaker than at the surface. So, their onboard atomic clocks naturally tick faster than clocks on the ground. But the satellites are also moving quickly, and special relativity says moving clocks tick slower. So, there are two competing effects. Gravity, weaker up there, makes the satellite clocks run faster. Speed, faster up there, makes the satellite clocks run slower. When you add them together, the gravitational effect wins. The satellite's clocks would drift ahead of Earth clocks by tens of microseconds per day if uncorrected, enough to create navigation errors that grow into kilometers. So GPS has relativity built into it, not as an optional feature, as a requirement. It's one of the cleanest everyday proofs that Einstein wasn't just telling a clever story. He was describing the operating system the universe actually uses. And it's worth lingering on that for a moment, because it's easy to underestimate what it means. Relativity is not only about astronauts and black holes. Relativity is sitting quietly inside your phone. It's inside the timing networks that help planes land and ships navigate. It's inside the synchronization that modern infrastructure depends on. Gravity's influence on time is not a distant curiosity. It's part of the reason the modern world stays aligned. Now, if gravity can change clock rates, it can also change the behavior of light. Because light is, in a sense, the messenger of time. Light carries frequency. Frequency is a clock. A beam of light oscillates a certain number of times per second. So, when a photon climbs upward out of a gravitational field, what changes is not that the photon loses something like a little object shedding weight. What changes is the relationship between that light's oscillations and the receiver's local time. From the perspective of the higher observer, the light arriving from below appears redshifted, lower frequency, longer wavelength. From the perspective of the lower observer, light sent downward would appear blue-shifted, higher frequency, shorter wavelength. Again, no need for mystical language. This is geometry meeting measurement. A useful way to picture it without getting tangled is to imagine light as a note played on an instrument. At the bottom of a gravitational field, an atom emits a note with a specific frequency. That note travels upward. At the top, the listener's clock is running faster. So, when they measure the incoming note, they count fewer cycles per second. The note sounds slightly lower, redshift, but the universe doesn't change the light in the way a hand changes a string. The universe changes the context in which the light is measured. The geometry changes how time slices the wave. That's why gravitational redshift pairs so naturally with time dilation. They are two sides of the same coin. And this is where the story starts to point toward the next kind of evidence. Because once you accept that gravity affects time and light, the leap to light bends is no longer such a leap. If space-time is shaping the paths that matter follows, and if light is not exempt from space-time structure, then light's path can also curve. Not because light is being tugged like a falling stone, but because straight in a curved space-time is not what your intuition thinks it is. Still, before we step into the sky and talk about starlight and eclipses, it's satisfying to collect what you've earned here. You've taken gravity out of the category of downward pull and moved it into the category of space-time behavior. You've taken time out of the category of universal background and moved it into the category of local experience. And you've seen how those two shifts connect. Stronger gravity means slower time. Weaker gravity means faster time. Light climbing out of gravity is redshifted. And the world you live in, the practical, ordinary world, quietly confirms these facts every day. If you want a final image to hold on to before the story continues, make it this. 2 clocks, one on the ground floor, one on the top floor. The building is still. Nothing is moving. No engines, no rockets, no storms. And yet, if the clocks are precise enough, they are not living in the same tempo. One is taking slightly longer steps through time than the other. It's the gentlest kind of difference, almost unfairly small. But it's real. And it's exactly the kind of difference that only a universe made of space-time could allow. Because in a space-time universe, gravity doesn't just tell matter where to go. It tells time how to flow. And once you accept that, the idea that light itself might follow the curves of gravity starts to feel not shocking, just natural. Light has a reputation for being untouchable. It has no rest mass, no edges you can grab, no handle. So, for most of human history, it felt safe to imagine light as the one thing that would travel through the universe in perfect, indifferent straight lines, like a ruler laid across the sky. And then gravity entered the story in a new way, not as a force with a hand, but as geometry. If space-time is the thing being shaped, and if straight means the straightest possible path through that shape, then light cannot be exempt. Because light doesn't travel through space-time the way a marble travels through a hallway. Light travels as space-time allows. It follows the rules of the landscape. And when the landscape is curved, even a perfect straight line can become a curve. That is the quiet, stunning claim at the heart of gravitational lensing. Not that gravity pulls on light like a magnet, but that light, like everything else, traces the geometry. It takes the path that is locally straight, what physicists call a geodesic, through a space-time that is not flat. If you let that idea settle, the next step becomes almost inevitable. If light can be shifted in frequency by gravity and delayed by gravity, then light can also be redirected by gravity. The sky, in a sense, can act like glass. Not because there is literal glass out there, but because space-time itself can behave like a lens. A lens bends paths, and a gravitational field, especially a strong one, reshapes paths. That's why gravitational lensing is so powerful. It takes Einstein's picture out of the realm of abstract philosophy and turns it into something you can see, not with your eyes alone, but with telescopes, images, and measurements that line up like footsteps in fresh snow. To make it feel natural, it helps to start with a small, everyday analogy, one that doesn't pretend to be perfect, but does give your mind something to hold. Imagine you're walking across a wide field in the fog. You cannot see the whole landscape. You can only see what's right in front of you. You try to walk in what feels like a straight line, always stepping forward, always choosing the direction that looks straight from where you stand. But the field is not flat. It slopes gently, then subtly dips, then rises again. Even if you never choose to turn, your path can bend because straight ahead is being defined locally, step by step, by the ground beneath you. That's close to what happens with light. A beam of light does not look ahead to the final destination and choose a path in advance. It simply moves forward at the speed of light, locally through the geometry that exists at each point. If space-time is curved, the local definition of straight changes from place to place. So the beam bends, not because light is being yanked sideways, but because sideways and straight are not globally consistent in curved geometry. That is what makes Einstein's claim both subtle and terrifyingly precise. Now, historically, the first major public demonstration of this idea came from a moment that feels almost cinematic: a total solar eclipse. The logic was elegant. If the sun's mass curves space-time, then light passing near the sun should follow that curvature. So, starlight from background stars, stars that are normally hidden by the sun's glare, should appear slightly shifted in position during an eclipse when the sun is blocked and those stars can be photographed. The stars haven't moved. The light has, or more precisely, the light's path has been altered by the geometry around the sun. In 1919, during a total eclipse, expeditions led by Arthur Eddington took photographs that suggested the starlight was indeed deflected, roughly in line with Einstein's prediction. It wasn't a perfect experiment by modern standards. Early measurements were challenging, and later history has debated how clean the data truly was, but culturally, it mattered. It showed the world a new kind of thinking. The universe is not a stage with actors moving on it. The stage itself participates, and light, the most faithful messenger we have, reveals it. Even if you ignore all the mythology around that eclipse and look only at the core point, the transition is powerful. Newton's gravity explained why planets move. Einstein's gravity explained why light moves the way it does. And the moment you accept that, something new becomes possible. You can use gravity to see things you otherwise couldn't. Because if mass bends space-time, and space-time bends light, then mass can distort the images of distant galaxies behind it. Mass can magnify. Mass can stretch. Mass can split one galaxy into multiple images. Mass can turn a faint smudge into a bright arc. That is gravitational lensing. It is nature's telescope, and it doesn't require mirrors or glass. It requires only gravity. At first glance, lensing can look like an artistic accident. A galaxy appears as a thin curved streak. A cluster of galaxies appears surrounded by faint, ghostly arcs. Sometimes you see what looks like a partial ring, a circle of light that seems too perfect to be real. Those are not camera glitches. Those are the sky admitting, plainly, that straight lines are not sacred. A gravitational lens can do a few distinct tricks, depending on how extreme the geometry is. In the gentlest case, the effect is called weak lensing. Nothing dramatic happens to a single galaxy. Instead, many background galaxies, thousands, sometimes millions, look slightly stretched in a coherent pattern. Individually, each galaxy is messy and different, but statistically, a pattern emerges. It's like looking at tall grass after a wind passes through. No single blade tells you the wind's shape, but the whole field does. Weak lensing lets astronomers map the distribution of mass in the foreground by measuring these tiny, systematic distortions. Then there's strong lensing, where the geometry is more intense and the alignment is just right. A distant galaxy can be warped into bright arcs. It can be magnified so much that you can study details that would otherwise be far too faint. It can even appear as multiple images, separated pieces of the same object, arriving to us along different paths through curved space-time. And in the rare, near-perfect alignment, you get something that feels almost unreal. An Einstein ring, a nearly complete circle of light around the lensing mass. It looks like the universe drew a halo with a steady hand, but it's simply symmetry. Light from the background source is bent around the foreground lens in all directions, and it reaches you as a ring. Again, not magic, geometry. Now, here's where the story becomes even more useful, because lensing does not care what the mass is made of. It does not care whether the mass is bright or dark. It does not require the mass to shine. It only requires the mass to curve space-time, which means lensing becomes a kind of cosmic honesty test. You can compare what you see, stars, gas, glowing galaxies, to what gravity implies is present, and sometimes the comparison is unsettling. Because the lensing map says, gently but firmly, there is more mass here than your eyes can find. This is one of the cleanest bridges into dark matter. Long before dark matter became a mainstream concept, astronomers noticed something strange. Galaxies rotate too fast for the visible mass to hold them together. Clusters of galaxies behave as if they contain far more mass than they appear to. But those were dynamic arguments, based on motion and inference. Gravitational lensing adds something else. It lets you map the mass directly through its effect on light. So, when lensing says, there is mass here, and the telescopes say, there is no light here, you are forced to take the possibility seriously. Something is curving space-time. Something is shaping the paths, and it's not showing itself in the ordinary ways. One of the most famous and emotionally compelling examples of this comes from colliding galaxy clusters. When two clusters pass through each other, their components behave differently. The galaxies themselves, mostly empty space, tend to sail through. The hot gas, which contains a lot of ordinary matter, collides, slows down, and lingers in between. If gravity were only coming from the visible matter, you'd expect the gravitational center to track with the gas because the gas contains most of the normal mass. But lensing maps often show something else. The strongest gravitational lensing signal, meaning the bulk of the mass, tracks with the galaxies, not the gas. It's as if most of the mass passed through without colliding, which is exactly the behavior you'd expect from dark matter. Matter that interacts gravitationally, but not much else. This is why lensing is so important. It's not only beautiful, it's decisive. It takes the idea that gravity is geometry and turns it into a measurement tool. It turns space-time into a scanner. It allows the universe to reveal the invisible by how it bends the visible. And once you start thinking this way, you begin to see lensing everywhere. Not always as dramatic rings and arcs. Sometimes it's a subtle magnification that makes distant galaxies slightly more visible than they should be. Sometimes it's a statistical shear pattern that only emerges when you average over huge regions of sky. Sometimes it's a time delay between multiple images of the same quasar, light taking different routes through curved space-time, arriving minutes, days, even years apart. Different paths, different lengths, different gravitational potentials along the way, different clocks in a sense. Even in lensing, time dilation is quietly present. Because when space-time is curved strongly enough to produce multiple images, it also affects how long light spends on its journey. The universe not only bends the path, it adjusts the schedule. And if you're listening in bed, letting the night soften your thoughts, there's a calm wonder in that. It means the cosmos is not merely distant scenery. It is an active geometry, a living shape. Every massive object you've ever looked at, Earth, the moon, the sun, a galaxy cluster, does not just sit in space. It shapes the straight lines that pass near it. Now, it's worth saying one important thing, so the picture stays clean. When you hear light bends, it can sound like light is being slowed down or dragged like a rope. That's not the right feeling. Locally, in its own neighborhood, light still travels at the speed of light. Always. What changes is the path it takes through the larger geometry. It's like a river flowing at a steady speed, but the riverbed curves. The water doesn't need to change its local behavior for the overall direction to shift. That distinction matters because it preserves the core of relativity. The speed of light is a local constant, even in a curved space-time. The bending is not a violation. It's the consequence of what straight means. And this is why lensing feels like such a perfect continuation of the story you're telling. Earlier, you replaced the picture of gravity as a pulling force with gravity as geometry. Then you showed time responding to that geometry. Now you show light responding to that geometry. And once light responds, the universe becomes readable in a new way. Because light is what brings us information. So, if mass shapes light's path, mass shapes what we can know. Lensing becomes a kind of cosmic handwriting, a way space-time leaves signatures on the sky. And the final bridge you set up in your outline is the most satisfying one. We can map mass we can't see because space-time still curves. That line works because it doesn't require hype. It doesn't claim we've solved everything. It simply states a fact. Gravity doesn't care about brightness. Space-time doesn't curve only for things that glow. So the bending of light becomes a ruler for invisible mass, a quiet method, a patient proof, and from here, the story can widen. From a 1919 eclipse to modern deep sky surveys, from simple deflection to arcs and rings, from pretty distortions to the unsettling realization that most of the mass in the universe may be dark. Not absent, not imaginary, just quiet, just unseen, still shaping the geometry, still guiding the light, still writing its presence into the paths that photons take across billions of years. And when you look up at a night sky that seems still, you can remember, even the emptiness between stars is not empty of structure. The universe is curved, and the light reaching you has been following those contours the whole way home. Gravity does its best work when no one is watching. Not in the dramatic moments, not in the scenes we turn into posters and headlines, but in the slow, patient shaping of ordinary matter over ordinary time. It doesn't hurry, it doesn't need to, it simply stays. And because it stays, it becomes the quiet architect of almost everything you recognize as a world. On the scale of Earth, gravity is not just the reason you don't drift away. It's the reason the planet has layers instead of being a uniform, unmixed ball. It's the reason oceans settle where they do. It's the reason the air clings to the surface like a thin, protective skin instead of evaporating into the black. Gravity shapes, gravity sorts, gravity sculpts. Picture the early Earth, not as a finished globe with continents and clouds, but as a chaotic blend of rock and metal, heat and debris. In that mess, gravity begins to separate the heavy from the light. Dense materials, especially iron and nickel, slowly sink inward. Lighter silicates rise outward. Over long stretches of time, the planet differentiates into a core and mantle and crust. Not because anyone decided it should, but because gravity makes down a real direction even inside a forming world. This is one of gravity's most underrated tricks. It creates pressure, enormous pressure. It squeezes matter into behaviors you would never see in a laboratory on the surface. Deep inside Earth, the weight of all the layers above compresses the layers below. and that compression becomes a kind of engine. It changes how rocks behave. It influences the way heat moves. It sets the stage for slow circulation, convection, where warmer material rises and cooler material sinks, not as a storm, but as a deep geological breathing. Gravity doesn't create the heat, but it decides what the heat can do with the materials it's trapped inside. That's why Earth is active, not frozen. Why the surface is not a perfectly smooth shell that never changes. Even if you only mention this gently, without turning it into a lecture, you can still let the listener feel the idea. Gravity makes worlds organized. It takes random ingredients and gives them a hierarchy. Heavy goes inward, light goes outward, gas becomes a sky. And that sky is not a small detail. An atmosphere is a fragile thing in space. It's a layer measured in miles, resting on a planet measured in thousands of miles, sitting beside a vacuum that is very eager to pull everything apart. If gravity were weaker, the atmosphere would leak away more easily. If it were stronger, the air would be denser, the pressure greater, the weather and chemistry different. The breathability of a world is not only chemistry, it is also gravity, quietly holding molecules close, giving them permission to linger. Gravity also makes water behave like water. It draws liquids into basins. It makes rivers flow downhill instead of wandering randomly through the air. It makes rainfall return to the ground. It gives the oceans their shape and their calm insistence, pulling them into a smooth surface that always wants to become level. And even when gravity is being gentle, it can still be felt in the motion of water in ways most people don't think about. Tides are one of the most poetic examples of gravity working at a distance on a living planet. The moon's gravity tugs more strongly on the near side of Earth than the far side, and the sun adds its own quieter pull. The oceans respond, slowly sloshing, rising and falling, not because the sea is restless, but because gravity is a gradient, a difference, a slope in space-time's influence. The tides aren't just water moving. They're the planet feeling its place in a larger gravitational conversation. You can stand on a shoreline at night and watch the tide come in, and you can be watching orbital mechanics made visible, a cosmic pattern expressed in foam and wet sand. Gravity shapes, gravity sorts, gravity sculpts. Now, if Earth is gravity's patient craftwork, the solar system is gravity's choreography. Because once you pull back from one planet and see the whole arrangement, you notice something almost musical. Stable patterns, repeating rhythms, resonances, gaps, rings, and the strange fact that order can emerge from a system that began as a rotating disk of gas and dust. A forming star collects most of the mass. The remaining material flattens into a disk. Within that disk, small grains collide and stick. Tiny becomes larger, larger becomes bolder. Gravity turns little clumps into growing seeds, and growing seeds into bodies large enough to clear neighborhoods, shaping their paths like someone smoothing wrinkles out of fabric. And then Jupiter enters the picture. Jupiter is not just the big planet. It's a gravitational presence so strong that it affects the architecture of the entire system. In many ways, Jupiter is a reminder that gravity doesn't only hold things together, it can also prevent certain things from forming simply by stirring the disk too much in one region, or by nudging orbits until collisions become too violent or paths become unstable. There is a place between Mars and Jupiter filled with asteroids, rocky debris that never became a planet. One reason is simple. Jupiter's gravity exerts persistent tugs that disturb that region. The asteroid belt is not empty. It's a population of leftovers, shaped by resonances, orbital rhythms where the timing of orbits lines up in ways that make the gravitational nudges repeat. If an asteroid goes around the Sun twice for every one Jupiter orbit, or 3 times for every one, those repeated tugs can become a steady push. Over long times, resonances create gaps, regions where you don't find many asteroids because those orbits are unstable. The most famous of these are the Kirkwood gaps, empty lanes carved by a planet that never comes close, simply by repeating the same gravitational whisper at the same point in the orbital cycle, again and again, until the pattern becomes visible. This is one of the most beautiful aspects of gravity. It creates structure not only through brute strength, but through timing, through repetition, through patience. It's a slow sculptor with a metronome. And if Jupiter is the heavy drummer in the background, Saturn is the artist who makes the sculpture visible. Saturn's rings look like decoration, but they are physics on display. They are countless particles, ice and rock, each following its own orbit, each obeying the same gravitational rules, each responding to tiny nudges from Saturn's moons. Up close, the rings show divisions and gaps and sharp edges, as if someone drew them with a careful hand. One of the most famous gaps is the Cassini division, a darker region between bright ring bands. It's not a missing piece by accident. It's connected to resonance with one of Saturn's moons. Again, gravity becomes pattern, a repeated tug, a steady shaping over time. Even more quietly, tiny moons, shepherd moons, help maintain the edges of rings, keeping particles confined, guiding them, preventing them from spreading out indefinitely. This is the kind of detail that makes the solar system feel less like a random collection of objects and more like a living clockwork. Not perfect, not fixed forever, but coherent. Now widen the view again, beyond the neat circles and rings, out toward the edge of the sun's influence. Far beyond the planets, there may be a vast reservoir of icy bodies, what's often called the Oort cloud. Not a tidy ring like Saturn's, but more like a distant spherical swarm, comets waiting in the dark. If this region exists as we think it does, it is another product of gravity's long-term sorting. Objects that were flung outward by early gravitational interactions, placed into long, slow orbits, so far away that a year becomes a number almost too large to feel. Out there, the sun's hold is weaker, and other influences begin to matter. Passing stars, the gentle tide of the galaxy's gravity, subtle nudges that can alter orbits over time. And sometimes, one of those nudges sends a comet inward, falling towards sunlight after eons of darkness. It becomes a visible visitor, briefly bright, briefly famous, leaving a faint trail like a signature. The comet didn't decide to come. The system arranged it. Gravity shapes, gravity sorts, gravity sculpts. And then, beyond planets and comets, gravity does something even more profound. It builds stars. It begins with clouds. Cold, thin, vast molecular clouds drifting through the galaxy. Regions where gas and dust are denser than average, but still incredibly sparse by earthly standards. Inside these clouds, small irregularities appear. A little more density here, a little less there. Maybe a nearby supernova shockwave compresses part of the cloud. Maybe a collision between clouds triggers a ripple of collapse. Maybe turbulence simply leaves a knot behind. However it starts, gravity responds to density. Where there is a little more mass, gravity is a little stronger. Where gravity is a little stronger, it pulls in more mass. And as more mass arrives, gravity grows stronger still. That feedback is the beginning of star formation. At first, it's almost imperceptible, a slow contraction, a gentle gathering. The cloud becomes a collapsing region, and as it collapses, it heats up. Not because someone turned on a heater, but because gravity does work. Potential energy converts into thermal energy as the material falls inward and compresses. This is a deep idea, and it's worth saying slowly. Gravity can make things hot simply by squeezing them. As collapse continues, the center becomes denser, hotter, more pressured. Eventually, a protostar forms, a young star still feeding, still surrounded by a disk. It's still gathering the last of its material. And then the central temperature rises high enough for nuclear fusion to ignite. That ignition moment is often described as a birth, but it's really a balance, because fusion does not replace gravity. Fusion fights it. Gravity pulls inward, fusion pushes outward through pressure. A stable star is not a tranquil object. It is a ceasefire. It exists in hydrostatic equilibrium, gravity compressing the star, pressure from the hot, fusing core, resisting that compression. It is an ongoing negotiation, and as long as the balance holds, the star shines steadily. This is another place where gravity's character becomes clear. It is not always an obvious downward pull. In stars, gravity is the reason fusion happens at all, because without that relentless inward pressure, the core would not reach the densities and temperatures required to make hydrogen fuse into helium. In a way, gravity is the match and the hand holding the match. Yet it's also the weight that keeps the flame constrained. And over a star's lifetime, gravity continues to shape the story. For small stars, the burn is slow. They sip fuel, glowing gently for trillions of years in some cases. For massive stars, the burn is intense and brief. They race through their lives in millions of years, building heavier elements in layers: helium, carbon, oxygen, neon. Each stage a new balance, each stage a new fight between pressure and collapse. Eventually, for the most massive stars, fusion cannot continue to provide enough outward pressure. The core can become iron-rich, and iron does not give energy by fusing in the same way. The balance fails, and when the balance fails, gravity takes over completely. Collapse happens quickly on cosmic terms. The star's core falls inward, pressure and density spike, and the outer layers can rebound violently. The result is a supernova, an event so bright it can briefly outshine an entire galaxy. It's easy to describe this dramatically, but for the tone of this channel, it can be held with calm wonder. A supernova is gravity's final act in the life of a massive star, and it is also one of the universe's main ways of making and distributing the elements that build planets and people. Because many of the heavier elements, iron, gold, iodine, the ingredients that make biology possible, are forged in stellar interiors and violent endings. They are not common in the early universe. They are created through generations of stars living and dying. So when someone says softly, "You are stardust," it doesn't have to be sentimental. It can be literal. The calcium in bones, the iron in blood, the oxygen that fills lungs. Those atoms were shaped by gravity long before they were shaped into you. Gravity shapes, gravity sorts, gravity sculpts. And there's a soothing perspective hiding in that repetition. Gravity is the same rule on every scale, yet the outcomes are so different. On Earth, it holds a thin atmosphere and gives oceans their patience. In the solar system, it organizes resonances and rings, gaps, and visitors from the dark. In the galaxy, it gathers clouds into stars, and stars into clusters, and clusters into the larger architectures that eventually lead to galaxies, filaments, and the web of the cosmos. It is one influence expressed in countless forms. And if you let your mind rest on that, it becomes easier to feel why gravity is such a central character in this whole journey. Not as a force that simply pulls down, but as the shaping principle that turns simple matter into structured worlds. It creates places. Not only locations, but environments, regions where certain behaviors become possible. Without gravity, there is no stable ocean, no settled sky, no long-lived star, no planetary system with resonant patterns. There is just drifting material, forever unassembled. And when gravity assembles things, it doesn't do it perfectly. It leaves scars and leftovers. It leaves belts of debris. It leaves eccentric orbits and inclined paths. It leaves comets sleeping at the edge of influence. It leaves rings that should spread out but are held in place by moonlets. It leaves planets that migrate and systems that rearrange themselves. But the overarching effect is still unmistakable. Gravity makes complexity possible by making structure persistent. And now, after walking through Earth and the solar system and the birth and life of stars, the listener can feel the ladder rising naturally toward the next ideas, toward black holes, where the curvature becomes extreme, toward gravitational waves, where the geometry itself carries energy outward, toward dark matter, where lensing reveals mass that won't glow, toward dark energy, where expansion accelerates, and toward the unresolved frontier, where quantum rules and gravitational rules still refuse to fully merge. But for this moment, it's enough to hold the simpler truth. Gravity is the reason the universe can build anything at all, and it is doing that building quietly right now, beneath every footstep, above every cloud, inside every star that still burns, and in every orbit that still repeats its patient loop through the dark. Some places in the universe don't feel like objects at all. They feel like rules turned up to their limit. A black hole is one of those places. Not a monster, not a cosmic vacuum cleaner roaming around and swallowing everything in sight. A black hole is something quieter, and in a way stranger. A region where gravity has reshaped space-time so deeply that the usual idea of escape stops applying. To understand that, it helps to hold one idea in your mind with gentle clarity. A black hole is not defined by what it pulls. It's defined by what space-time allows. There is a boundary, an edge, that isn't made of matter, and yet it matters more than a solid wall. That boundary is the event horizon. The simplest way to picture it is as a line drawn on the map of space-time. Outside the line, there are paths that lead outward. Inside the line, every future-directed path points inward. Not because something reaches out and grabs you, but because the geometry of forward has tilted. If space-time is the stage, the event horizon is where the stage becomes steep in a very specific direction. Light is the key, because light is the fastest messenger the universe permits. If light cannot climb out, nothing can. And when you say it that way, you can feel why the horizon matters. It's the place where escape would require going faster than light, which is not an engineering problem, it's a rule. Now here's the surprising part. The size of that horizon is not determined by how dense the black hole is at the center. It's determined primarily by mass. The simplest black hole you can imagine, one that isn't spinning and isn't charged, has a characteristic radius called the Schwarzschild radius. It's the distance from the center at which the event horizon would sit. You don't have to memorize the formula to feel the meaning. More mass means a larger horizon. A black hole with the mass of the sun would have an event horizon only a few kilometers across, something like the size of a city. That's a mind-bending thought all by itself. The sun reduced to a horizon the size of a small region on Earth. Meanwhile, supermassive black holes, millions or billions of solar masses, have horizons that can be larger than the orbits of planets. Their gravity is intense, but the edge can be unimaginably wide. This already hints at an important nuance. Black holes are not suction machines. They don't reach out farther than any other object with the same mass. If you could replace the sun with a black hole of the same mass, an impossible swap, but a useful thought experiment, Earth's orbit would remain essentially the same. The gravitational influence at Earth's distance would be the same. The big difference would be simple and devastating in a different way. No sunlight, no warmth. The sky would change, not because gravity suddenly became stronger at our orbit, but because the sun's light would be gone. This myth-busting matters because it returns black holes to physics instead of folklore. They are extreme, yes, but they're still governed by the same gravitational story we've been building. Objects follow space-time's geometry. So, what happens as you approach that horizon? This is where black holes become not only powerful, but deeply counterintuitive. Time behaves differently. In general relativity, gravity doesn't just curve space. It changes the way time flows. Clocks near a massive object tick more slowly relative to clocks far away. Near a black hole, this becomes dramatic. From the perspective of someone far away, watching from a safe distance, an object falling toward the horizon appears to slow down. The signals it sends take longer and longer to arrive. The light it emits becomes more stretched and faint. In that distant viewpoint, the falling object seems to hover, dim and fade. It can look like it never quite crosses, but that's an effect of perspective, of how time is sliced up between observers. For the person falling, their own clock is normal. Their heartbeat, their thoughts, their sense of now continues. They cross the horizon in a finite amount of their own time. There is no sudden impact with a surface at the horizon. The horizon is not a physical shell. It is a boundary in the structure of possible paths. And that contrast between what the distant observer describes and what the falling observer experiences is one of the cleanest places to feel general relativity in your bones. Reality is not a single camera angle. Spacetime makes perspective part of the story. Now, when people talk about black holes in a frightening way, they often jump to the word spaghettification. It's a vivid term, and we can keep it gentle by focusing on the idea rather than the imagery. The core concept is tidal gravity. Gravity is stronger, closer to a massive object. So if you have an object with length, anything extended, one end can be pulled more strongly than the other. That difference in pull can stretch and compress. Near Earth, tidal forces are mild. They're strong enough to move oceans. They're not strong enough to tear you apart. Near a small black hole, tidal forces close to the horizon can become enormous because the gravitational gradient changes rapidly over short distances. That's where the stretching effect becomes extreme. But here's another nuance that calms the picture. For supermassive black holes, the horizon can be so large that the tidal forces at the horizon can be relatively gentle. The gradient there can be smaller. The edge is far from the central region, where curvature becomes truly violent. So even the famous danger of tidal forces depends on the mass and the scale. Black holes are not one thing. They are a family of geometries. And at the center of this geometry, deep within, general relativity predicts something called a singularity, a region where density becomes infinite and the equations break. But that infinite is less like a destination and more like a warning sign. In physics, infinities often mean a model has reached beyond its valid domain. General relativity is stunningly accurate, but we don't expect it to be the final word at arbitrarily small scales. The singularity is nature telling us, something is missing here. This is where black holes become not just astrophysical objects, but philosophical pressure points. They force our two best frameworks, general relativity and quantum physics, into the same room. And the room gets tense. Before we go there, one more piece of the black hole story deserves quiet attention, because it's almost poetic in its own right. Black holes are not perfectly black, not in the deepest sense. In the 1970s, Stephen Hawking discovered that when you combine quantum field theory with the curved spacetime around a black hole, something unexpected happens. Black holes can emit radiation. This doesn't mean matter is blasting out from the inside in a dramatic stream. The picture is subtler. In quantum field theory, empty space is not a simple void. Fields are present everywhere, and their lowest energy state still has quantum behavior. Near the horizon, the boundary between inside and outside changes how these quantum fields behave. The result is what we call Hawking radiation, a faint thermal emission that allows a black hole to slowly lose mass over time. It's one of the strangest sentences in modern physics. A black hole can evaporate, but if you're imagining a rapid disappearance, you can let that go. For stellar mass black holes, the timescales are beyond ordinary comprehension, far longer than the current age of the universe. A black hole with the mass of the Sun would take on the order of 10 to the 67th years to evaporate through Hawking radiation. That number is so huge it barely functions as a number. It's more like a reminder that the universe is comfortable with patient processes. So in practice, black holes stick around. They merge, they grow, they sit quietly at the centers of galaxies. Hawking radiation is real in theory, deeply supported by the way quantum fields work in curved spacetime, but it's extraordinarily faint for large black holes. Still, the existence of Hawking radiation changes something fundamental, because if a black hole can evaporate, then the story of everything that fell in becomes unavoidable. And that's where we arrive at the famous puzzle, the information paradox. Here's the calm version of the problem. Quantum mechanics has a principle that, roughly speaking, information about a physical system is not destroyed. The exact statement is technical, but the spirit is simple. The universe keeps track. The present is connected to the past in a reversible way at the deepest level. General relativity, meanwhile, describes black holes in a way that seems to erase details. To an outside observer, a black hole can be described by only a few numbers: mass, spin, charge. Everything else about what fell in looks like it gets hidden behind the horizon. Now combine that with evaporation. If the black hole eventually radiates away and disappears, where did the information go? Did it leak out in the radiation, somehow encoded in subtle correlations? Did it remain trapped, leaving behind a remnant? Was it destroyed, forcing us to revise quantum mechanics? Or does the very concept of inside and outside need rethinking at the quantum level? This is not a small academic discomfort. It is a crack that runs through our understanding of reality because it puts two extremely successful theories into direct conflict. General relativity describes spacetime as smooth geometry. Quantum physics describes nature as probabilistic, discrete in certain ways, and fundamentally encoded in wave functions and fields. Black holes sit at the intersection. They are gravity turned up high enough that quantum rules can no longer be politely ignored. And this is why black holes belong in your storyline, even in a gentle, sleepy channel. Not because they're scary, but because they are the cleanest, most elegant place where the universe whispers, "You don't have the full picture yet." If Newton gave us the math for gravity, and Einstein gave us the meaning of gravity as geometry, black holes are where Einstein's meaning becomes unavoidable, and where the next step waits, still unfinished. They also serve another purpose in the arc of the episode. They prepare the listener for gravitational waves. Because black holes don't just sit there, they can dance. Two black holes can orbit each other, lose energy, spiral inward, and merge. When they do, the event is not primarily a flash of light. Often it's dark in electromagnetic terms, but it's loud in space-time itself. The geometry ripples. Reality rings like a bell. So in these few minutes, black holes quietly do three things at once. They show what space-time curvature looks like at an extreme. They challenge our intuitions about time and observation. And they force quantum physics and gravity into a conversation that is still ongoing. And if you want one last gentle anchor line to leave the listener with, something that feels like the channel's voice, here it is. A black hole is not a place where gravity becomes a stronger pull. It's a place where forward becomes a direction you can't turn away from. Not a cosmic mouth. A geometric boundary, a rule written into space-time. And in the quiet after that thought, it becomes easier to imagine the next idea, that space-time itself can carry waves, and that we have learned how to listen. If black holes are the quiet proof that space-time can become steep, then gravitational waves are the proof that space-time can also become restless. Not restless like a storm, more like a deep ocean, so vast and steady that you forget it's there, until a distant ship passes, and the whole surface carries a faint, organized swell. That's the feeling to hold on to tonight. Gravitational waves are not waves in space. They are waves of space and time, ripples in the geometry itself. And the strange thing is, we predicted them long before we could ever hope to measure them. Because once you accept Einstein's central move, that gravity is geometry, another idea becomes almost inevitable. If geometry can curve, then changes in that curvature can travel. A moving mass distribution shouldn't just rearrange the shape of space-time locally. It should send out a kind of news into the universe. A gentle disturbance, a traveling pattern, a ripple. But here's the first reason gravitational waves can feel unbelievable. Gravity is weak, so weak that even dramatic cosmic events only wrinkle space-time by an almost unimaginable amount by the time the signal reaches Earth. That's why gravitational waves stayed in the realm of theory for so long. Not because Einstein's math was unclear, but because nature's signal is so delicate. To build intuition, imagine two heavy objects orbiting each other. Not just planets, something far more compact. Two neutron stars, for example, or two black holes. As they orbit, they accelerate, and accelerating masses in Einstein's picture can radiate gravitational waves. That radiation carries energy away. And if energy leaves a system, the orbit changes. The two objects spiral closer, their orbit speeds up. The waves grow stronger, the frequency rises. Then, finally, there's a moment where the two become one, a merger. In the last instance, the system can release an enormous amount of energy, not mainly as light, but as gravity waves, a surge of space-time motion that travels outward at the speed of light. This is the key. The universe doesn't just contain events like that. The universe responds to them. It rings. Now, long before any laser interferometer existed, there was an elegant, indirect way to test this idea. In the 1970s, astronomers found a special kind of system, a binary pulsar. A pulsar is a rapidly spinning neutron star that beams radio pulses like a lighthouse. And because those pulses are so regular, they become a clock in space. If you track the timing carefully, you can see whether the orbit is changing. And in a famous case, often associated with Hulse and Taylor, the orbit was shrinking at a rate that matched what general relativity predicted if the system was losing energy through gravitational wave emission. It was like watching the wake of a boat without seeing the boat itself. Not the direct ripple, but the unmistakable bookkeeping, a calm, precise confirmation that something real was leaving the system. Still, the dream was to detect the waves directly, to catch the ripple itself. And that brings us to the most delicate measurement task humans have ever attempted. Because by the time a gravitational wave reaches Earth, it doesn't throw objects around the way a regular wave might. It doesn't knock over buildings or shake the ground. It passes through nearly everything. Instead, it does something subtler. It stretches and squeezes distances. Not by much, not even by a billionth of a percent. By a fraction so small that it sounds like a metaphor. A gravitational wave slightly lengthens space in one direction, while slightly shortening it in the perpendicular direction, then reverses back and forth as the ripple passes. And the only way to detect this is to measure distance with exquisite precision over kilometers, while removing every ordinary vibration you can imagine: traffic, wind, tiny thermal motions, even distant ocean waves rumbling through the planet. This is where LIGO enters the story. Two L-shaped detectors, widely separated, each with long arms, kilometers in length, using laser light to measure whether those arm lengths change relative to each other by an almost impossibly small amount. The idea is simple enough to say out loud: split a laser beam, send half down one arm and half down the other, reflect them back, recombine them. If the arms are exactly the same length, the returning light lines up in a predictable interference pattern. If the arm lengths change, even slightly, the interference changes too. In other words, light becomes a ruler so sensitive it can notice space-time itself breathing. And yes, people sometimes describe the sensitivity in a dramatic way, like a tiny fraction of a proton's width. The precise phrasing can vary, but the point is consistent. This is measurement at the edge of what feels physically possible, which is why the first direct detection felt like science fiction becoming paperwork. In 2015, LIGO observed a signal that matched the signature of two black holes merging. The waveform had a recognizable shape, a chirp, low and slow at first, then faster and stronger, then a final ring down as the newly formed black hole settled into a stable geometry. That last phrase is worth savoring, settled into a stable geometry, because that's what the ring down is, the newborn black hole vibrating, like a bell that's been struck, shedding its distortions and gravitational waves until it becomes smooth again. And in that event, something mind-bending happened in the accounting. A few solar masses worth of energy converted directly into gravitational radiation. Not as matter flung out, not as a bright flash, but as space-time motion itself. For a brief moment, the power output in gravitational waves outshone all the stars in the observable universe combined, though, again, not in light you could see, in geometry. It's hard to hear that and not feel a quiet awe. And then, only a couple years later, another milestone broadened the story. In 2017, gravitational waves were detected from a neutron star merger, and telescopes also saw the electromagnetic aftermath. This was multi-messenger astronomy, the same event experienced through different channels, gravity waves and light. And neutron star mergers are special. They don't just test relativity, they also touch the origin story of the elements. These collisions are thought to produce heavy elements: gold, platinum through intense nuclear processes. So, with one detection, you get a physics confirmation and a cosmic narrative. Geometry ripples, matter reshapes, elements scatter, and the universe becomes more chemically complex. But for our purposes, this quiet, sleepy, step-by-step journey, the deeper takeaway is simpler. Gravitational waves turn general relativity from a beautiful explanation into an instrument. They gave us a new sense, like suddenly being able to feel distant events rather than only see them. Because gravitational waves don't care about darkness or dust in the same way light does, they pass through regions that would hide electromagnetic signals. They carry information about motion and mass in a direct way. They let us observe the universe's most extreme dances, even when the stage is unlit. And one more gentle thought can settle in here. When a gravitational wave passes through you, it's not really pushing on you like a gust of wind. It's briefly changing the geometry that defines distance and time in your region of the universe. You remain you. Your atoms remain bound. Your heartbeat keeps its rhythm. But the space-time between parts of the detector, between mirrors, between reference points, shifts by an amount small enough to be safe, and yet large enough to be measurable with the right kind of patience. So, what does it mean emotionally to live in a universe like that? It means the universe is not static. It's not a silent container where events happen in isolation. It's a connected fabric, capable of carrying echoes. Somewhere, far away, two dark objects meet, and long afterward, without any light announcing it, the geometry around you whispers, "It happened." And as we move forward, this whisper becomes a bridge. Because if space-time can ripple, if reality can vibrate, then the next question almost asks itself, what is space-time made of deep down? And what happens when the ripples meet the quantum rules? That edge is still ahead, but the fact that we can detect the ripples at all already tells you something extraordinary. The universe isn't just understandable, it's measurable, even when it's speaking in the softest possible voice. There's a quiet confidence in gravity, not the loud kind, not the kind that demands attention the way lightning does, or the way a roaring engine does. Gravity doesn't announce itself. It simply keeps happening, everywhere, all at once, patient and relentless, like a rule the universe never forgets. And that's what makes the next truth feel so strange. General relativity has passed every test we have managed to throw at it. It predicts Mercury's subtle drift. It explains why time runs a little differently on mountaintops than it does at sea level. It tells light how to bend, and it lets us read the invisible shape of mass across the cosmos. It even foretold the existence of ripples in space-time, gravitational waves, long before any instrument was quiet enough to hear them. So, if it works so well, why do physicists keep saying, with a kind of careful reverence, that gravity still isn't finished? Because there's another framework, just as successful in its own domain, that doesn't fit cleanly with gravity's story. Quantum physics. Quantum theory is the instruction manual for the small. It describes atoms and electrons, light and fields, the jittery, probabilistic texture of reality at microscopic scales. It predicts the behavior of matter with breathtaking precision. It's the reason we understand chemistry, semiconductors, lasers, whole chapters of the modern world. But when you try to make gravity speak quantum, it starts to stutter. In quantum physics, forces usually come as particles, as quanta, little packets that carry interactions. The electromagnetic force has photons. The strong force has gluons. The weak force has W and Z bosons. Gravity, if it were a force in the same style, would have its own quantum messenger, a graviton. And maybe it does, but we haven't seen one, not even close. Part of the problem is that gravity is astonishingly weak compared to the other forces. If you want a sense of that weakness, just remember that a small refrigerator magnet can overcome the entire gravitational pull of Earth on a paperclip. That doesn't mean gravity is unimportant. It's the architect of planets, stars, and galaxies. But at the level of single particles, gravity's quantum signature would be unbelievably subtle. The deeper problem is more conceptual. General relativity doesn't place gravity inside space-time. It says gravity is space-time's geometry. The shape of the stage is the thing doing the work. Meanwhile, quantum physics usually assumes the stage is fixed, like a quiet backdrop where fields and particles perform their dances. Trying to merge those ideas is like trying to write a single story, where the paper itself is also a character, where the page can ripple, tear, fold, and rearrange, while the ink is already busy being uncertain. That's why quantum gravity isn't just a missing equation. It's a frontier in what it even means to explain. Over the last century, 3 broad approaches have risen to the surface, not as final answers, but as different ways of aiming a flashlight into the dark. One approach is string theory, which suggests that what we call particles are tiny vibrating strings, and that gravity appears naturally as one of the possible vibrations. It's a sweeping idea, elegant in its ambition, and it changes the question from what is a graviton to what is the underlying object that can vibrate into everything we see. Another approach is loop quantum gravity, which takes the geometry of space-time seriously from the start and asks whether the fabric itself might be quantized, built from discrete chunks, like a weave made of loops. In that view, space-time isn't infinitely smooth. It has a smallest kind of stitch. A third family of ideas suggests something even more unsettling, that gravity might be emergent, not fundamental at all, a large-scale effect, like temperature, made from deeper microscopic rules. No single molecule has temperature, but trillions together do. Maybe gravity is the same. Maybe the curvature we experience is what a deeper information like reality feels like when viewed from far away. None of these ideas is confirmed. That's not a failure. That's the honest shape of the edge. And what's beautiful is that the edge is not just philosophy. Physicists design experiments that might one day touch it. They look for tiny deviations in how gravity behaves at very small distances. They listen to black holes and neutron stars as if they are cosmic instruments, hoping extreme gravity reveals a faint quantum accent. They explore delicate laboratory setups where small masses might be placed into quantum-like situations, searching for a sign that gravity can participate in quantum rules without breaking them. It's slow work. It's patient work. It's the kind of work that mirrors gravity itself. So, if you want to hold on to a few calm takeaways before the night carries you further down, gravity isn't simply a pulling force. It's the shape of space-time guiding motion. Freefall is what happens when nothing resists that guidance. Weight is the sensation of being pushed off your natural path. Time and light respond to gravity because they live inside the same geometry, and we've measured that again and again. Black holes and gravitational waves aren't just science fiction. They're confirmations that the geometry is real. And beyond all of it, quantum gravity remains the open door, quietly waiting at the far end of our best understanding. If you've enjoyed this gentle journey, you can leave a comment with a topic you'd like to drift through next, and subscribe if you want more nights like this. And now, as you rest, you can let one last thought settle in, softly without needing to hold it too tightly. You are not being pulled downward by an invisible hand. You are simply moving along the contours of space-time, while the earth beneath you rises up to meet you. And in that simple meeting, between your path and the ground, gravity becomes a feeling. Good night.